So we will continue with our discussion on demodulators for binary modulation schemes. Yeah, maybe one possibility is that we can, I think I can try to have it ready by Monday morning. Yeah, no, I'll try to give you by Monday morning, and I think other thing I'll talk about after at the end of the class. Okay, so as I said, we'll continue our discussion on demodulators for binary signaling. Just to recapitulate for what we were doing last time, we had discussed coherent receivers for antipodal signals first, and we discussed a number of possible realizations for it, right? Starting with baseband realization, then passband realization, using match filters, using passband and baseband match filters, and also a correlator implementation, right? And then we went on to looking at the coherent demodulation of orthogonal signals, binary orthogonal signals, right? And we looked at a very general simple case. Well, the general mathematical result that we looked at was that in this case we need two match filters, a bank of two match filters, one match to each of the two waveforms that you are going to use in the orthogonal signaling scheme, all right? And the overall receiver structure will then have a system by which the incoming signal is match filter using each of these two filters and then mutually compared. The output, the sample output at each signaling instant t equal to LT is compared from both the outputs, or for comparison you can even subtract them out and then see which one is larger, right? So that was a basic idea, and this is a very simple depiction for the case when you are taking your two signals to be real, two orthogonal signals to be real. For that case when the signals are complex, of course one can just generalize this picture very easily by just putting a conjugate there, right? But one need not do that, and I'll talk about that a little bit more, but let me fully revise for you what we did last time. The mathematical equation for this is you compute the output of the first match filter as well as of the second match filter, take the difference, and depending on which is larger you declare that either a 1 or a 0 was transmitted, right? This was the mathematical equation that we looked at corresponding to that structure. Of course you must remember that each of these output quantities u sub 1 and u sub 0 is associated with some noise, and therefore there is always a likelihood that occasionally this noise value may disturb or may disturb the polarity and make us arrive at a wrong decision. Of course we hope that if our signal to noise ratio is reasonably good, the probability of occurrence of such events will be small, but we will look at the detailed performance analysis in terms of error probability a bit later. So this was what we discussed last time. To continue from here, as I said, let's first try to look at the general picture when we replace this with complex orthogonal signals, right? Complex orthogonal signals, well, the same structure is valid except that you put conjugate over here as we just discussed, but that would kind of imply that, of course we will also have a complex input signal to deal with. At the moment I have simplified the whole thing by just taking a real input signal, but then if I take this as complex, this as complex and this as complex, everything is valid, right? But if you recall, one of our results that we discussed when we discussed the match filter properties was that at the sampling instant the response is always going to be real, right? So although if you implement it in the most general form, you will have to do a complex valued processing throughout. Our final interest is not in a complex valued output. Our final interest is only in a real valued output which occurs at the sampling instance. Is it clear? So even when one has complex valued orthogonal signals here and complex valued input, one need not really compute the complete complex valued outputs of the two filters. It's sufficient if you compute only the real valued outputs, because finally we are going to look at these outputs only at the sampling instance, at which time instant the value is anyway expected to be real. The imaginary component is expected to be 0, right? So we need not compute that, or we need not process in a manner that requires more processing unnecessarily, and that is what is shown here. The baseband realization of coherent I'm sorry, yeah, okay, that's fine, of coherent FSK. That is, of course, I am calling any orthogonal scheme as FSK here, right? So you see what is happening? You have an incoming real signal which is first represented in its complex form by quadrature demodulation, right? By demodulation with cosine and sine. So you get the complex envelope of the input signal, which you now process through a pair of complex filters in such a way that you only produce a real output, right? That is, ideally I would have had a complex input here and a complex output here, complex input here and a final two valued output here, but I am only computing a real value at each of these two filters, at the output of each of these two filters. So how do you take the real value? How do you compute the real value? Take the real part of this, convolve it with the real part of the impulse response. Similarly, the imaginary part, convolve with the imaginary part. These two added together will give you the real part coming out of the first complex filter, corresponding to S minus T, S sub O minus T. S sub O minus T has two parts, the real part and the imaginary part. All right. So you basically have the real part computed here for the S O minus T, and similarly the real part computed here for S 1 minus T. Okay. So you take the same signal multiplied by S1 or not multiply, convolve with S1 or convolve the imaginary part with S1I and add the two together to give you the real. Naturally, because one in phase
and the quality phase component,
yes,
both of them are real, is not?
Right. The input is real, sure, but how do you get the complex representation in the first instance?
No, they are the components of the corresponding complex waveform,
right?
Waveform.
Correct.
But we haven't introduced a J component. I mean, it is like if it is SR and SI, the complex waveform is SR plus JSI.
I think I discussed at the end of the last class also, and in general, when we discuss the passband representation, the significance of this cosine sine demodulation, the quadrature demodulation. How do we obtain a complex envelope representation of a real passband signal? So finally what we have here is this plus j times this. The received signal, which is passband in nature, is now represented in baseband form by this complex waveform. Complex means this is the real part, this is the imaginary part, right? And what I am now saying is, so therefore, if you take the analogy, basically we have the input now, where the input is complex. In this picture, the input is complex. This V now becomes complex, right? And this V now corresponds to this pair of signals. All right? This pair of signals could have been processed precisely as shown over here by the use of complex valued filters here, which we are doing here, but we are just modifying the processing slightly so as to compute only the real parts of each of these two filter outputs rather than the full complex parts, full real as well as imaginary parts. we need to compute two outputs, one corresponding to this filter, one corresponding to this filter. In general, each of these two outputs is going to be complex, right? But I'm computing two outputs, this and this. This constitute the first filter, complex valued filter. The real part is here, the imaginary part is here. It's valid on the complex valued input. It's processing the complex valued input. But I'm only computing the real part, right? For the imaginary part, I should have also done some other combinations, right? I should have passed this through this through this, and then combine those two, which I'm not doing, right? Is it clear? Similarly, for the other filter, I'm again processing the real part and the imaginary part so as to produce only the real output.
So
okay.
Shouldn't the output of S0 1
Yes.
S0 IT minus T subtracted from the S0 R minus T?
There is a conjugation to be done when you are convolving, right? The input signal, when you, if you remember the basic equation,
Okay.
this VT conjugate, there is in the convolution. The representation is such that we are conjugating one of the signals before carrying out the convolution, right? And therefore that sign takes care of that. Any other problem? So this is a baseband realization of a coherent FSKT model. I hope you have understood it. If not, please let me know, and we can go over the portion which is giving you trouble again.
So why are we exactly adding it S0R and S0I? We should square and add. Square the
Why square?
Because energy we want.
No. That is automatically going to come out of the match filter output. We already seen.
Yeah.
Okay. Why should we square? Right? There is no need for squaring here. Basically, I am computing the match filter output and comparing it with thresholds. That's all I am doing, as I am supposed to do in coherent receivers, right? And in coherent receivers, what's the basic idea? That is, phase is exactly assumed to be known or exactly compensated for, so that we don't have to worry about the unknown phase. We discussed that at length earlier, and we'll return to this when we go from coherent to non-coherent. Dipankar? Anybody else?
Can you do some mathematical analysis?
The mathematics is same. The mathematics is precisely the same as I have done earlier. There is no difference. The required equation is precisely this. That is, I need to compute U1 and need to compute UO, and I need to compute the values at a sampling instance. Now, in general, these U1 and UO would be, U sub O would be complex valued, but at the sampling instance they are real valued. Therefore, I am only computing the real parts. That's the mathematics, nothing more than that. Okay. You know how to compute only the real part of a complex product. You multiply the real number with the real part, imaginary with the imaginary, and either add or subtract the two, depending on the nature of the two complex numbers. Of course, here we are not multiplying, we are convolving. That's the only difference, right? So that's precisely what is happening here. Okay, so if that is fine, that gives you an idea how to do demodulation of coherent demodulation of FSK, frequency shifting, or any sort of orthogonal binary waveform at baseband. First, bring the signal to baseband by quadrature demodulation, and then process like this. Okay. Of course, alternatively, if you wish, you could do the whole thing at passband itself, and in that case, you will have to implement match filters at passband. Right. So this is an alternative to this. This is the original baseband realization. Alternative is do everything at passband. Don't take the real signal which is coming in at passband and process it by two match filters at passband itself. And a general form of these match filters is going to be as shown here, isn't it? S sub O R minus T cosine 2 pi f naught T plus S sub O I minus T sine 2 pi f naught T. Same thing, except that we now have the indices S sub 1 over here. compare the two outputs at the sampling instant and then decide which one was transmitted, 1 or 0. Fine. Any questions on passband realization? Basically, you have two filters. Suppose your orthogonal signals were consisting of two frequencies, right? Which are mutually orthogonal. Two signals at different frequencies which are mutually orthogonal to each other over the signal duration. Then essentially it will boil down to having one tune filter at one frequency and the other tune filter at the other frequency. This is what it will boil down to. Right? Of course, I have got here a general representation. I have not really looked at what is the nature of these orthogonal signals, S source, I mean this particular signal. But if it is truly FSK, then this will boil down to the impulse response corresponding to frequency F1, and this will correspond to impulse response corresponding to frequency F2. Right? That will make you choose this S sub OR and S sub OI in such a way that this corresponds to an impulse response or a passband filter at F1 and another passband filter at F2.
So what are the input to the two filters in this case?
Input is a received FSK signal.
No, the filter is real in filter response is real in its.
At passband, yes, everything is real. That's the whole idea. When you are doing passband, you are working with real signals throughout, right? That's why you need to work with quadrature components directly. The whole idea of going from passband to baseband is to go first to a complex representation through quadrature demodulation and then do complex valued processing. This point you must absorb very clearly. I thought by now you would have got used to the idea of complex representations because you have been doing it since your previous semester. The complex valued representation is typically used to obtain a low pass representation of a passband signal, right? So when you want to do baseband processing, you first convert your passband signal to baseband representation. How do you do that? You do quadrature demodulation, right, by cosine and sine of the carrier. However, if you want to do processing at the frequency at which the signal is coming in or at an intermediate frequency, some passband frequency, you can continue to work with real valued signals as they come in, right? There is no need to do any quadrature demodulation in that case because you are going to work at that particular frequency, and which one would be preferable will depend on the application you are working at. For example, if you are working in the microwave band with a large bandwidth, and it may be very difficult to work at baseband, but because even if you bring the signal down to baseband, the bandwidths of those signals may be very high, and your baseband components may not be able to handle that kind of bandwidth. Whereas it may be relatively simple to make tune filters match to those frequencies at the microwave itself. Special components can be perhaps made, like SAW components or other components, surface acoustic waves, and many other possible technologies are available depending on the frequency at which you are working. You could directly realize this filter with the possible technology at passband itself. However, in many other situations, it may be more convenient to first bring the signal down to baseband and do complex valued processing, and then you can use digital signal processing.
So you said that actually these two will be two tune filters corresponding to.
They could be, provided you have a true FSK signal, in the sense that this corresponds to transmission of a particular frequency F1 and this corresponds to transmission of a particular frequency F2, right? In that case, these complex envelopes will be so chosen that this essentially becomes an impulse response of a tune filter. Well, if you, I think you have forgotten what we discussed long time ago, basic binary orthogonal modulation schemes. Many times you just refer to any orthogonal signaling scheme as FSK in a loose way, right? So this is a treatment for that situation, right? In the specific situation when you are actually transmitting two different frequencies to generate your orthogonal set of signals, then essentially they'll boil down to two filters tuned to two different frequencies.
This may generally be a BPSK or whatever.
No, not BPSK. BPSK is not orthogonal, it is antipodal.
Okay, QPSK or
Even QPSK is not orthogonal, right? You look at other orthogonal signals we discussed there. We discussed many possible examples of orthogonal signals, right? I gave you a number of possible waveforms which could serve as orthogonal signals, right? For example, this could be a pulse with with impulse response like that, and other pulse like that. These two signals will be orthogonal over a particular time interval, let's say from here to here, right? And we discussed many other schemes, but the most important one remains FSK out of all this, practically speaking, right? So that brings us to the end of our discussion on coherent receivers for binary signals. What is left is some kind of an understanding of their performance, but I like to look at them together, both for coherent as well as for non-coherent. So I'm postponing it slightly, right? We like to look at the so-called receiver structures that we have looked at. How do they really perform in the presence of noise? What kind of signal to noise ratios are required to obtain reasonable error rates, right, which may be acceptable? So that kind of analysis we still have to do, and we'll do that after some time. But first let me now go over to the class of receivers which one has to worry about when phase is not known to you properly, and that is non-coherent receivers. Again, at the moment only for binary signals. Okay. Now, if you remember our discussion on coherent versus non-coherent, we said that there are some situations where we may not be able to either estimate the phase, or its estimate may turn out to be too bad, and therefore it will be now not possible to compensate for the unknown phase shift that may exist between what is transmitted and what is received, right? And therefore you don't have a perfect knowledge of the incoming received signal, at least to the extent of a phase shift, right? There may be other problems, but at the moment we are only discussing this problem due to the presence of an unknown phase shift between what is received and what you thought might have been transmitted. Because after all, your match filter impulse response assumes a knowledge of phase, right? It assumes complete knowledge of the signal. Only then you can design a match filter for it, right? If the signal is ST, the match filter is S minus T, S conjugate minus T. So you have to know the ST precisely in every little detail except possibly for amplitude, because scaling doesn't matter, right? But in every other sense you must know the signal perfectly, and therefore one can use this match filter concept that we have discussed so far only in the coherent situation when phase is either known or can be estimated reliably.
The phase shift not being known, that means that the signals which actually you are receiving, there may be some nonlinear change of shift between from symbol to symbol,
or is it some kind of a delay kind
or
of thing?
simply
It's
a
some
delay?
kind of a it is not exactly, see, if it was a pure carrier it would have been a delay, but there is a modulation also in it, so it represents some kind of a distortion, some kind of a distortion at the input, which carries on or goes on to the output in the form of bad performance, which we have tried to appreciate. For example, you may remember at the passband coherent receiver, if you have a slight delay, if your sampling instant is not correctly chosen, it is offset by a small amount, right? Your output will fall considerably, so much so that at a spacing of 1/4 f naught it becomes 0, right? In an unknown phase shift will cause that kind of an effect.
So is
Right.
that unknown phase shift random?
Typically it is, there can be two kinds of models, deterministic as well as random. Both models are used, right? And wherever convenient you model it as random, wherever convenient you model it as deterministic but unknown.
It varies
Right.
from time to time.
Deterministic means it's a constant value which is not known to you. That is a deterministic model. The other random model which is typically used is it's a random value which may lie anywhere with equal probability, let's say between 0 to 2 pi. Right? Both kinds of models are possible and are used.
The point is that it varies from time to time. I mean, that is
Depends on how this phase shift is occurring. It really depends on the mechanism of that phase shift. Right? For example, it may be due to a fluctuating medium. The path length may be varying with time between the transmitter and the receiver. Or there may be unknown phase shift sources within your antenna, within your receiver, which may be contributing to this phase shift. Right? And so depending on the overall situation, one may use an appropriate model. At the moment, I'll not say more than that, but at a later time, when we possibly do carrier recovery or something, we can take that up in more detail. But to returning to what should we do when this is a situation. Now, one thing is clear, that in this kind of a situation, the rules of signaling schemes, the use of those digital modulation schemes which put information in phase is kind of ruled out, isn't it? If to start with, in your modulation scheme, you are putting information in phase of the carrier, and at the receiver you say that your phase is not exactly known, then it kind of implies that you should not use those modulation schemes in such situations. Right? So, use of antipodal signaling schemes like BPSK is ruled out. Of course, one can do something even in these situations, but I will talk about that separately. Right? But therefore, really speaking, it makes more sense to talk of non-coherent receivers for binary orthogonal signals, where typically information is not embedded in phase. Information is embedded in signal shape itself, right? Either possibly in the form of choice of different frequencies or some other attributes, but not phase, right? So this is something that you must keep in mind. Anyway, let's start with a general passband signal which has some phase shift. We'll have a real part modulating the cosine carrier which is associated with some unknown phase shift theta, and an imaginary part with sine 2 pi f naught t plus theta, right? Or if you were to write the same thing in the complex envelope form, just for convenience I am not going to use a different notation. I think it is clear from context what it means. In the complex baseband form, I could as well write this as VRT plus J V sub IT into e to the power j theta, right? Strictly speaking, I should be using different notations for these two, right? But since it does not cause any confusion, I will continue to use identical notation, right? So we have this situation. In the coherent case, we got around this by saying theta is exactly known, so I can eliminate this by multiplying this received signal with e to the power minus j theta, right? Or equivalently a passband by doing coherent passband demodulation, right? Fine. Now let us, to understand this case better, I will take a very simple signaling scheme, the simplest possible, and that is on-off keying. On-off keying is a special case of, do you remember which class of modulation schemes? On-off keying? Orthogonal, right? It's a special case, and it's a simplest special case because orthogonality is by virtue of using a zero signal as one of the two signals, right? So it's one of the simplest possible orthogonal signaling schemes that you can have. Simple waveform, very rarely used now, but very convenient for the purpose of understanding first simple things. So it's a simple waveform, and I'll simplify it further because I want to just develop the basic concept. Let's assume that it's a very simple scheme in which even VIT is 0. So our transmitted signal is VRT cosine 2 pi f naught t plus theta. That's all. I mean the received signal, right? And your VR is obviously going to be a stream of pulses let's call them, I'll call the pulse shape AST when noise is absent. Right? When noise is present, VRT will also contain some noise. Let me consider noise absent situation just to develop the basic concept. So, is the model with which we are working clear to all of you? We are taking on off gain as the starting example. In that also we are simplifying things further by removing VIT. So, basically we have VRT which will contain both signal as well as noise. The signal is, let us represent it by AST, which is essentially a stream of, this VRT is a stream of pulses in the absence of noise, which will be either coming with 0 amplitude or with some amplitude A, right. So, more precisely I can write the received signal Vt in the absence of noise over 1 bit interval, right, as either this plus this or 0 . Fine. Does that cause any confusion? I am writing the complex envelope of this signal at baseband, right. VIT is 0, but we have a phase shift which will be in the complex form represented by e to the power j theta, right. So, basically what we receive is AST into e to the power j theta, which is what I have written here, AST cosine theta plus JA ST sine theta. This is when your corresponding bit AL is 1 and this is when it is 0. If you transmit a 1, this is how you will be receiving the signal. If you transmit a 0, this is how you will be receiving the signal over 1 bit, whichever bit interval you have selected. Of course, this is in the absence of noise. Alright. If you want to extend this to multiple bit intervals or general situation, well, we can then write simply a summation A sub L S, how do I modify it? T minus LT cosine theta, I am assuming phase shift to be constant throughout, this whole thing multiplied by cosine theta plus J times same thing AL ST minus LT into sine theta, when of course you are transmitting a 1. If you are transmitting a 0, it is 0. After you are done match filtering on this, suppose I go ahead and do the simple plain match filtering that we have been talking about so far. Okay, what will be the output of that match filter? Output of the match filter, let me denote that by U sub t, UT. Well, it will be simply this waveform convolved with the match filter corresponding to the waveform ST, because what you know is ST, not the actual received waveform, right. And let that response be RT, what we have been using so far, right. So, this will simply become A sub L R T minus LT cosine theta plus same thing into sine theta, alright.
So, this is in case we use a match filter.
In case we use a match filter, this is the output of the match filter. And finally, what are we going to do with the match filter if we continue to proceed along the strategy we have developed so far. We'll sample the match filter output at the kth sampling instant, t equal to kt, because I have used L as a dummy index here, so I'm not calling Lth sampling instant, right? L is the dummy index in this, so I'll use some other index k. I'm going to sample it at some time instant kt and then decide whether in the kth interval this or that was transmitted. All right. Let's look at the sample value at t equal to kt of this. All right. What will be the value? What will be the contribution from this summation? If we are using Nyquist pulses, then the contribution will only come from a sub k, right? Similarly from this. Assuming that we are using Nyquist pulses, that is your ST is such that the response of the match filter is a Nyquist pulse, right? That then if I sample this output at t equal to kt, the contribution from this summation will come only from the term a sub k, because all other terms will contribute a zero value at t equal to kt, because r kt minus lt would be 0 for k not equal to L. All right. So let's assume that in that case at t equal to kt we can write u of kt equal to, tell me the answer, a sub k cosine theta, right, plus j times a sub k sine theta, right? Now you know what to do. I don't know theta, I can still get what is a sub k by just taking the magnitude, right? Okay, so that by taking this simple example, I wanted to tell you how to obtain your a sub k, even when you don't know theta, right? So take mod of u sub kt, and that gives you your a sub k, the value of a sub k. Of course, if it is 0, then it will be 0. If not, it will be that particular amplitude. All right. Of course, strictly speaking, I should write this, because when you take the mod, you will have to take the squares, sum of squares, and then square root. The sign will really go, but then that doesn't bother us. We are using orthogonal signaling scheme, right? Either it will be 1 or it will be 0. Fine. So what does that tell us? What should be our structure? Our structure is we continue to use our match filter as before, but follow it up with, what is this operation? Taking a modulus of a complex representation, envelope detection, right? So follow it up with envelope detection. That's your optimum receiver. This is also sometimes called non-coherent match filter. Okay, in which the phase information is ignored by taking the envelope information, by doing this kind of processing. So this is what you do for the case of on-off keying. This is a baseband OOK receiver, on-off keying modulation scheme, demodulation for that, non-coherent demodulator for that. You have your incoming passband signal, obtain the complex baseband representation through quadrature demodulation, have this match filter S minus T to obtain the real and imaginary parts, and then square the real imaginary parts, sum them up, take the square root, sample at t equal to kt, and make your decision.
So should the sampling be after the squaring operation, or can it?
Well, one can do either way. It hardly matters. It depends on how you want to implement it. Whether you want to have samplers here and follow it up with, it hardly makes any difference, because basically you are interested in the sample value of this envelope at that instant. Whether you continue to have a continuous envelope detector and then sample the output, or other way around, makes no difference, right? Whichever is easier for you to do.
The detector will be not polarity detector, but will have a threshold.
No, actually this is just a notation. This is a threshold detector in which the threshold will now lie between 0 and some amplitude, right? It will not be at 0. The threshold will not be at 0. It will not be a polarity detector. I have just indicated it as a standard threshold detector. It is a notation for threshold detector. It should be interpreted that way. Whether don't let this confuse you. Fine. And if you want to do a passband implementation, tell me what will it be like, so that I don't start from here, but I start from here. What do I need? Suppose I want to do this thing directly at passband without bringing the signal down to baseband first. I have a passband match filter followed by an envelope detector, which is very easy to build, which you have done in amplitude modulation, demodulation in your analog modulation scheme. A simple diode and an RC arrangement can be used for that envelope detection, right? In that situation, of course, you can't do that at baseband implementation, because for that you have to have a carrier for that to work.
How exactly is it done in this case?
In this case, you have to implement all these things.
No, how for instance will we implement this amplitude?
Everything is done in baseband.
Match filtering as before. Here you realize
No, the latter portion.
the latter portion. This is some basically some non-linearity which you have to implement, right? One can devise a circuit for it, or if the whole thing is being done at baseband, the present trend is to do everything digitally, right? And then this becomes a simple digital
So
computation.
then envelope detection is a misnomer for it, because it actually is
When carrier is present.
when a carrier is present, then you detect the envelope of the carrier.
No, but now we are interpreting envelope detection as a more general operation of this kind, right? This is our definition of envelope detection in this case. That is, we are taking the modulus of this complex quantity, right? It's a matter of nomenclature. You may call it whatever you like, but you must understand what we mean.
The pulses were used that to be orthogonal and Nyquist.
That's right. In fact, at the moment we are considering a very special situation of orthogonal signaling where one of the two signals is 0, right? We'll soon generalize it to the general case where we can have arbitrary two orthogonal signals, right? But before that, sorry, this is wrong. I should. I don't have it here. In fact, it is this only. Yes, this should be okay. This is wrongly written. Okay. If you want to do the demodulation at passband, you have a match filter directly at passband, follow it up with envelope detector, sample it at t equal to kd, and have a threshold detector. Okay, that's an alternative realization for the same problem. Okay, now let's try to generalize it for general signals.
Just one point, sir.
Yes.
In the previous baseband implementation, why did you have to square root it? When it's 0, so 0 is 0.
Really speaking, it doesn't matter very much,
Doesn't matter.
because you see, I square rooted it because of this equation. I wanted to implement this equation, but as far as your performance is concerned, it will hardly make any difference whether you square it or you don't square it. I mean, whether you square root or don't square root it, but the corresponding threshold will have to be modified, right, appropriately. Depending on what you do here, you will have to modify the threshold here.
Signal to noise would be better if you don't square root it.
I don't want to go into that discussion. There is some difference. It's very minor. It's less than a fraction of a dB. It's very small difference.
So what they give you 1 or 0?
Hmm?
The AK output is 1 or 0.
Yes.
So squaring, root squaring will not matter much. And even the threshold.
See, just I'll let you have a very small brief discussion since you raised this point. I didn't want to discuss that. what we have done here is basically derived the receiver from our intuitive point of view. I mean, we just try to appreciate what the signals are like at the output of this match filter, and then what we should do with it so as to obtain what we want to do. But there is a formal way of obtaining this receiver structure as an optimal receiver structure by following the methods of detection theory or hypothesis testing I briefly talked about some time ago. If you follow those techniques formally, you actually get this receiver structure as the optimal receiver structure. Okay. Now, whether you do this, whether you do the square rooting or whether you don't, will hardly matter if you are only considering signal, but this may have effect on how the noise will behave, right? And therefore, your overall performance may depend slightly, because there is a non-linearity here. If everything was linear, we knew, I mean, hardly would make any difference, but there is nothing. This is a non-linearity here, and non-linearity will behave now differently with respect to signal and differently with respect to noise, right? And one has to take care of that, because if you square root, you may have a Rayleigh distribution here. If you don't square root, you may have an exponential distribution there for noise, right? So that will make the difference to the performance. When we look at the performance comparison, you will try to appreciate this thing better. Okay, we'll come to that a little later. But I think you can see that in the presence of noise, the presence of this nonlinearity is going to behave differently when you have the square root and when you don't have the square root. But fortunately, if you adjust the threshold appropriately, the difference in performance turns out to be unimportant. It's very small. Okay. What we wanted to do now was to generalize this to the case of a general orthogonal signaling scheme, say FSK. That is, we want to develop non-coherent orthogonal receivers, non-coherent FSK receivers. Okay. Now, I think it's simpler if you look at this first and try to generalize this first, the passband structure. Can you tell me how would you like to generalize it for the situation where I have two possible orthogonal signals for 1 and 0? One signal representing a 1 and the other representing a 0. It's obvious now. I have two match filters, one matched to each of the two waveforms, each followed by a corresponding envelope detector, and now I compare the two outputs as before. Right? Very simple. So that's the picture here. Non-coherent FSK demodulator at passband. Okay.
Orthogonal, any FSK means orthogonal signal.
Yes. Basically, what it means is these two waveforms are, these two impulse responses or the corresponding input waveforms are mutually orthogonal. All right. Each of them followed by an envelope detector to get rid of the unknown phase problem, and then compare the two.
So in this case also you have taken the imaginary part to 0.
In this case, when you are taking the envelope, there is no question of imaginary part.
So for that.
No, at this point, this is a passband implementation. So there is no question of an imaginary part anyway.
Corresponding.
I'm coming to that. There is no, at least at passband, one doesn't work with a complex representation.
I'm not.
Earlier we had a S0R and S0I.
Yes, but not at passband.
We
Sir,
had the passband.
The representation is in terms of SR and SI.
SR and SI are components of a particular S. That's all.
S0R and S0.
That's right.
S0R and S0.
This is what I had earlier.
We don't have this. We are only using cosine term here. We don't using sine term here.
Oh, you could do that. You could add that to generalize this further. Yes, no problem.
By imaginary I meant the quadrature part.
Yes, but then you say that.
Okay.
Okay, because there is no imaginary component here. It's a real signal. Yes, you could generalize it further by putting an S0 minus T or SI minus, this could be SOR, and you could also add an SOI sine 2 pi f naught t. Right? You could generalize it further. Sure. Okay. This is slightly less general, but I think conveys the idea equally well. Well, basically what you have to do is take this old coherent FSK demodulator, put envelope detectors here. That's all we are saying. right? And that's what I got represented here. Now, how will you modify the baseband receiver? Let me show you the baseband receiver that we have just discussed. Yes, this is the one, isn't it? This is your complex input signal, followed by a complex valued match filter in general. Of course, in this case, it turned out to be a real valued match filter because S minus T is both, because I have taken a very special situation, and then take the mod square of this. Well,
I think the problem is we are taking the magnitude here.
yes,
In the earlier case, also the Passman version also. We
Yes.
take the magnitude.
yes,
Then we are comparing the two magnitudes from the S0 and S1 comes.
yes.
Then we are comparing the magnitudes. How do we say that the polarity?
Threshold.
What's okay?
Okay, because one of them is going to be there and the other is not going to be there. You are transmitting only one of the two signals in a particular bit interval. Only one of them will be larger than the other. In fact, one will produce a zero output, the property of match filters, right? And the other will be producing an amplitude A, right? Which is what you are trying to look at. Same good old way as you are doing coherent demodulation, except that you want to get rid of the unknown phase problem through this magnitude operation, annual detection operation. Just a minute to let's see generalization of this. Can you visualize it? Complex signal coming. All I have to do is have is duplicate this. One for S sub O and the other for one for S O, one for S sub 1, right? And that's a picture here for you. You start with a complex signal. If you look at this, this part and this part, this is doing the operation for S0, and this part and this part is doing the operation for S1, right? That's all. And then annular projection, comparison, right? This and this corresponds to SO, this and this correspond to S1.
Again, now this is again the real signal.
No, this is a complex signal. That's why I have got 4 channels here.
Real and
Okay, in this case I have taken real signal because I have taken SO to be only consisting of real part. One can make it more complicated by also considering the real and imaginary parts, right? And then take only the real part. I have slightly simplified the situation by considering the signal itself, the baseband signal itself, to be essentially real.
Yeah.
And this coming up, this representation coming up because of an unknown phase, right? I just simplify the situation slightly for you. But one can make it more complicated by taking a more general situation. There is no need. Okay, I have skipped the maths for this, a little bit of that, but that's very easy. And in any case, we'll take it up when we do the analysis. So next time, what I'll start with is analysis of this binary coherent and non-coherent receivers we've done so far. And after we have done that, we'll go over to a brief discussion of Emory receivers, right? Yes, on Monday. One more announcement I have. Your miners are ready for delivery.